Today we're going to have two back-to-back talks about extend basic lattice problems, go beyond them, and do even cooler things that we know how to do with basic lattice problems. And I guess it's up to us to figure out if these extended problems are secure, or we can do it from basic lattice problems. So cool things.
Thanks everyone for coming. So I'm going to be talking about optimal broadcast encryption and ciphertext policy from evasive lattice assumptions. So to begin with my slides from Simon's 2015. So the same old motivating scenario. Suppose we want to do sedating in the era of big data, which is like thank you. We're very old. It doesn't work anymore. Right. So you have a user who wants to join some website and is interested in online dating. So the first thing the user does is to create a profile which contains sensitive information about them. I don't know, where they went to school, where they live, etc., etc. And they like to limit access to this profile, ideally to people who satisfy their dating criteria. So for instance, something like this, or to keep up with the times, a PhD in crypto. So right, so users join the website, and when they do, they have different attributes. Oh, my light gray isn't showing. There's some light gray. Yeah, it shows up over there. Okay, it's not that important, I don't think. Right, they have attributes that say something about themselves, and then when they join the website, they get a secret key that's specifically tailored to the attributes. And the basic correctness requirement is that you have a key that satisfies the attribute, and for an attribute that satisfies the dating criteria, you should be able to decrypt the profile. And otherwise, for everyone else who doesn't, they should learn nothing whatsoever about the profile, even if they collude. So they shouldn't be able to mix and match their keys in such a way that allows them to cheat. So this is basically the notion of attribute-based encryption. Concretely, this is actually the ciphertext policy version because the policy F is on the ciphertext. So more generally in CPABE, we have a sender who holds a function F and a message M and wants to encrypt a message, and secret keys are associated with bit strings. And the basic correctness requirement says that you should be able to decrypt and learn M if only f of x equals 0. Okay, so here 0 is true and not equal to 0 is false. And this should hold even if there are collusions. Okay, so about a decade ago now, we showed that you can actually get ABE for circuits, so very expressive policies, very expressive functions F from the standard LWE assumption. So in the context of this talk, I'm going to call LWE B as B plus E, so S is on the left. I'm going to use squiggly underline to denote plus noise. So this is the LWE assumption, and this scheme is actually what we call a key policy scheme. But it does but using universal circuit, it gives you actually a ciphertext policy AB as well. So it does solve this problem, except that your ciphertext sizes are very large. Your ciphertext size is going to be roughly the circuit size of F. So recently, there's been a flurry of works trying to address this limitation and trying to get the CPABE with small ciphertext. In particular, they get ciphertext that's polynomial in the depth of the circuit times the length of the input x. Okay? So think of the depth of the circuit as roughly logarithmic in circuit size. So this is really a polylogarithmic in circuit size, or more generally sublinear in circuit size. Okay? And now these constructions don't quite get LWE anymore. They get LWE plus a little bit more. And depending on which set of results, the first set of results, in particular, these results are interesting. Well, they're independently interesting, but they also yield a solution to what's called optimal broadcast encryption schemes. So in broadcast encryption, we have a set, the F is a set of end users, and the function essentially corresponds to set membership. Okay? And here, if you have a CPABE of this kind of parameters, you get broadcast encryption schemes where your parameter size is polylogarithmic in the total number of users, capital N.
Get around the polydepth by, say, making circular security assumptions or other strong assumptions. This is like an inherent limitation.
Can you get around the
polydepth? You cannot, like in FHG, you cannot make a circular security assumption and get around the polydepth restriction, right?
And make a circular security assumption and get around the yeah. I don't know how to get I don't know how to get I don't know how to get ABE by making security assumptions. So let me try to say a bit more once you see that. So so one reason for doing this is to get broadcast encryption with optimal parameters. And let me now quickly say what kind of assumptions do these schemes use. So the first set of these results basically get CPABE for log depth circuits and C1, and they use LWE plus pairings. Essentially, they use a generic group model, but you can that part can be relaxed to some kind of knowledge assumption. But basically, LWE plus pairs. Okay, so you need a little bit more than LWE. So the second of these results gives a construction from lattice heuristics in the sense that it only uses lattice algebra, but the paper does not give a reduction to a simpler assumption. So in this sense, yeah, we don't even know how to, for instance, reduce the security of this scheme to some kind of circular security assumption. So it's sort of the state of the art for CPABE for circuits with small ciphertext size. And in this work, we give a new CPAB for circuits with small ciphertext size. In fact, our ciphertext size is slightly smaller, but that's not the main thing here. But we look at it from new lattice assumptions. So compared to the first of these works, we got rid of pairings, and we get to, I guess, arbitrary depth circuits. And compared to the second of these works, we actually get to a somewhat simpler lattice assumption.
It's on the length of X.
Yeah, we don't define the length of X. Yeah, we don't have it. Yeah. You'll see in a second. Right. Okay. Good. And right, as a corollary, we also get optimal broadcast encryption from these new lattice assumptions. Right. Okay. As a warm-up, let me give you a quick warm-up to our construction. The warm-up part is the same as prior works. So the starting point is this what we call this key equation that underlies all prior AB for circuits. But this is the equation that we were trying to talk about 8 years ago now, I guess. So basically, this equation says that, so on the left-hand side, you should think of A minus X tensor G as a shorthand of AI minus XIGs. You've seen these expressions before. Just this expression just says that, roughly speaking, starting from a very wide matrix A, you can derive some matrix A sub F that depend on your circuit F. And then this expression, you can recode A minus X tensor G to AF minus F of XG. So the starting point of construction is the following. Our master public key is going to be A. So the width of A is going to grow with the length of X. And the CAM, we're going to put A sub F into the CAM. And we're going to put A minus X tensor G into some combination of the ciphertext and secret key. Particularly, the CAM is an LWE sample with respect to A sub F. So the squiggly underlines for plus noise, as is a random encryption randomness. And we're going to make sure that we're going to design the ciphertext and the secret key in such a way that the product is the LWE sample with respect to A minus X tensor G. Concretely, the way we do this is we're going to publish an additional matrix B in the master public key. The ciphertext is going to be LWE sample with respect to B. So think of B as having standard n times n log Q. And your secret key is going to be random Gaussian pre-images with respect to B of the target A minus X tensor G. Okay? So in particular, if you multiply these two of them together, you get S times X tensor G. Right? So notice that the ciphertext size, because B essentially has fixed width, so the ciphertext size is independent of the length of X. And the dimension of all of these are going to depend on circuit depth, just because inherited from the key equation.
So why are you doing this again? If you didn't do this,
I'm just doing this just to get a scheme that satisfies correctness. Right, so this is our basic scheme. And in fact, you can show that you can get correctness for this scheme. If you multiply the two of them, you get S times A minus tensor G. You use this homomorphic evaluation, you can recover the CAM. And in fact, you can show that this scheme is secure if the adversary only gets one secret key, provided B is much wider. But right, this is sort of the starting point of the prior constructions. At least for BK20, the starting point of these two constructions is actually epsilon more complicated. But this is basically the basic construction.
So your point is that before you did this B and B inverse, right?
The problem
The
is
ciphertext depended on both F and X. So you
yes,
want to
the product of the ciphertext and secret key depend on X and X.
that's
You have to make sure that the ciphertext doesn't depend on X.
Sure.
So you move the X part into the secret key, and you make sure that your ciphertext doesn't depend on X. What's the secret key? This is your secret key.
No, but what is secret in that secret key? The
What's the secret in the secret key? The randomness used for Gaussian sampling.
B inverse is the
B inverse is a random Gaussian pre-image, such that B times this state, B times this Gaussian is A minus X tensor G.
When you say B inverse, what do you mean by B inverse?
Good. It's a random Gaussian, such that B times this Gaussian is equal to A minus X tensor G.
So B inverse is normal prime. There are many. Yes, that's
Yeah.
right. It's an operator.
So B times U equals to P. This is the Gaussian, a sample Gaussian. And I call this expression B equals to P. So it's a randomized image. So to compute this expression, you need a trapdoor for B. So master secret key is trapdoor for B, and then you're using the secret entropy is the randomness used for Gaussian fields. So that's no other secret randomness. So this is our basic scheme, and you can show that it's secure if you only given one secret key. And in fact, it's easy to see that this scheme is insecure if you get two secret keys. Roughly speaking, if you multiply the ciphertext by the secret key, the same LWE secret S appears twice, you can essentially recover S. Okay. So the approach from prior works to try to get a scheme that's secure against multiple secret keys, against collusions, is to try to, in some sense, randomize your S so that when you try to do this partial decryption, you get a different SIs for every new secret key SKI. Concretely, in the BV candidate, so Brakaski and Vaikuntanathan, SIs of the form are Ri times the square matrix S. Where your square matrix S is going to be your new encryption randomness, and your Ri is essentially going to be Gaussian, and it's going to be a Gaussian that comes from the secret key. So this ensures that this SI changes every time we try to do decryption, and at least will prevent the attack. So this is the scheme. This is going to be the approach we're going to take. So what we want to do is to design a scheme such that the product of the ciphertext is of the following form: R times S times A minus X times 3. Okay. So without the R, that's the one key secure scheme that we started out with. But this is the one we want to get, so that the S in some sense changes every time we do a new decryption. Right. So the main difficulty of achieving this decryption invariant is that you have a quantity that depends on the ciphertext stuck in between quantities that depend on the secret key. So you cannot decompose it into something that depends on the ciphertext multiplied by something that depends on the secret key. So BV gives a very clever way to realize this invariance. So they use some techniques from identity-based encryption, but that's not what we're going to do. Instead, we're going to rely on a very fairly simple matrix identity. This matrix identity in the literature is what's called vectorization. So basically what this says is that instead of working with the matrix S, you work with what's called the flattened version of S, which is the row vector you get from concatenating the rows of S. What this allows you to do is it allows you to move S from the middle to the left-hand side. So now S appears on the left-hand side, but in this form, and then your R moves to the other side with an extra tensor.
Just writing it down as a multilinear sequence of multilinear polynomials, and then sort of rewriting it.
Wait, who came up with this?
No. I'm saying this is just sort of writing the thing on top as a sequence of multilinear polynomials.
Yeah.
It's cheating. You made matrix multiplication commutative somehow.
Yeah. Yeah. Okay, so this is what we're going to do. I mean, this particular variant is easy because this thing is essentially a row vector. The more general version is slightly different. Right. So the nice thing about this is that now S appears on the left-hand side and R and X appear on the right-hand side. Okay. So now we can apply the same paradigm from before. We can decompose this into the product of a ciphertext and a secret key. So now in your new ciphertext, that's going to be B, and your LWE secret instead of being S is going to be the flattened version of S, which is a row vector. And your secret key will have an extra tensor times R. So this gives us the following CP-ABE scheme. Very simple CP-ABE scheme. And to the best of my knowledge, there's no attack on this scheme. So the main difference from the previous scheme is that now you have this extra randomization R that comes from a tensor product. For correctness, you actually need to publish R in the clear. So the only hidden entropy here again is as before is actually the randomness used for Gaussian pre-images.
Like the major difference from before is now you're taking B inverse of something that's real and not uniform, or it doesn't look.
Right, good. In the previous scheme, if you look at one secret key, the marginal distribution, if you ignore the master public key, is uniform. Yeah. Now it's inherently not uniform.
So even one key security is not clear.
Yeah, I don't know how to prove one key security from LWE. But BV has the same problem. Yeah, you're right. I don't know how to prove one key security from LWE. That's a good approach.
But R is not necessarily public, right? You don't have to make it.
R needs to be short for correctness.
Sure, but it's not public.
So for our scheme, we use Gaussians, and you'll see why.
Wait, no, is R public or is R not public?
Sorry, R needs to be short for correctness.
But public, is it public?
R is public. You need R to be public for also for correctness. So basically, what happens is that when you evaluate this whole thing, you get R times S times A sub F.
Right.
And then you only have S times A sub F here, so you need to multiply with R.
Okay, but I'm confused about something like pretty fundamental. So like, you said like, okay, this is problematic. This ciphertext times secret key equals R times S times other stuff because the secret key is on two sides.
The secret key is on two sides. That's why I'm making correctness.
But R's public, so it's not.
R is public, yes. Yes, okay, good. I'll show you in a second
Okay,
why.
okay.
So the intuition, no, okay. Roughly speaking, sorry, let's go back here. The intuition here is that you can treat R as an LWE matrix, public matrix, then R times S is pseudo random. So it's okay when R is public.
Oh,
That's roughly the intuition. Yeah, I'll come back a second to question.
So even if you don't make R public, can't you recover R? Like if you multiply B with,
So you need R to be public for correctness.
okay, but even if you don't explicitly make it, you can still recover R from.
Yes.
That's reading also.
Yeah, because basically when you do decryption, when you do homomorphic evaluation on this, you get R times S times A sub F. Whereas your CAM doesn't depend on R, so you need to multiply. Basically, you do this two together, you get R times S times A sub F, and then you multiply this by this, you get R times A times A sub F. It's a Diffie-Hellman type of number.
And R is shared or?
R needs to be low norm, and then for our scheme, we're going to make it
Is it the
Gaussian.
same for everybody or?
No, sorry, good question. It's a fresh R for every secret key. Yeah, that's where your randomization comes from. Yeah, that's a good question. That makes sure that when you multiply different secret keys together, you get R times S, and the R changes so you don't end up with the same S. That's how you avoid the previous attack. And the intuition about why this might be useful is the same as in BB. In BB, R needs to be public also. Basically, the intuition is that you treat S as your LWE secret, and then R times S is your random, even if R is public. That's roughly speaking the intuition. Great question. Any questions? This basic scheme, correctness should be somewhat clear. And the real question is true.
I have a question. We came to the use
Maybe
of,
these are my Eurocrypt slides, so we should make it happen.
we are trying to figure out security, but probably we're like starting where we started to use R because you're saying it's insecure to use the same to use the same vector as when decrypting multiple secret keys, right? Because you can have the same X with xi equals to 0 and xi equals to 1,
Exactly.
and you get S.
Yes.
So now we move to using R, but then what if I have multiple secret keys and they all have their independent R? Doesn't that allow me to recover the big matrix S multiply with the rest?
No, it doesn't.
No, it doesn't. So where does
But
it?
there's noise also.
Think of it as noise. Think of it as Ri transposes plus noise.
So you get some extra noise over here that prevents you.
You don't get to recover Ri transposes, but rather that plus noise.
Yeah.
And then LWE should kick in, where R is the public matrix, like low norm public matrix, S is the high norm secret matrix, and that's actually okay. You can switch back and forth. Yeah.
The attack doesn't actually recover S, you recover S times G plus noise. And because of the G, you can get rid of the noise. But maybe a bit easier to take this offline.
Isn't the same noise reused? Doesn't it come up in like CT times SKI for different noise?
I'm sorry.
Doesn't the same like error come up in CT times SKI?
The errors are really correlated, isn't it?
Yeah.
Yeah, the errors are
That's
really
a great
correlated. Yes, but as far as I know, there is no attack. So since there's no attack, the question is what can we prove about this? And okay, so let's try to prove something about this. So as a warm-up, let's try to prove that the product of the ciphertext and the secret key is pseudo-random. In fact, the product of many ciphertext and many secret keys are jointly pseudo-random. Okay, If we can prove this, this essentially rules out the previous attack because the previous attack really only uses the fact that you can multiply the ciphertext by the secret key. That's the first thing we're going to try to do. Okay. We should go boils down to showing that this expression is pseudo-random. Again, we have a different RI for every secret key. All right, so what's the first thing we'll do? Our intuition behind why randomization works is from LWE. So we're going to start with the LWE assumption that says that RI times S plus noise is pseudo-random, even if you're given the RIs. And pseudo-randomness will continue to hold if you multiply the left-hand side and the right-hand side by a low norm vector.
Sorry, again, you mean the squiggly? Was that the squig? Oh, okay, got it.
Yeah, this is pseudo-random. The joint distribution across multiple secret keys, even given RIs.
Yeah.
And this will hold even if you multiply things on both sides by a low norm vector, by a low norm matrix. You need it to be low norm because there's actually error.
But A is not low norm.
If A has low norm.
Okay.
If A has low norm and you replace G by I, then this is true.
Right.
Then this is pseudo-random. And then now on the right-hand side, you get different S's. You can now do a hybrid argument over the LWE secrets and get the right-hand side pseudo. Sorry?
S has high norm, right?
That's the only
S
thing
has
that-
high norm, RI has low norm.
Yeah, that's high norm.
Yeah. Yeah, S has high norm, R has low norm. And I only know how to prove this statement if A has low norm. If A has line norm, it could be true, but I don't know how to prove. All right, so this is good. This almost achieves what we want, except now we have to work with A with its low norm. Okay, and turns out this key equation that we have from before works even if A has low norm and when you have identity instead of the gadget matrix. Okay? The only problem now is that your noise growth, instead of being singly exponential in circuit depth, it's going to be doubly exponential in circuit depth. Because you don't get the savings from the repeated genes. This whole thing works. In fact, here this equation is even easier. You don't do the G inverse. You just whenever you multiply, you just multiply. Whenever you add,
because of no G inverse, the noise
becomes it's like the early version of GLWE. Yeah, so you get exponential circuit depth. Every time you multiply with every multiplication gate, your norm double. Your norm squares, so your exponential circuit depth. So if you naively plug into the previous construction, you will get ciphertext and secret key sign that's exponential in depth instead of polynomial in depth. So right, so for general circuit, this is not terribly interesting because roughly speaking, we already know how to get CPABE where the ciphertext and secret key sign depend on the depth of circuits. But it's sufficient for broadcast encryption because broadcast encryption corresponds to circuits with extremely low depth. In fact, the depth is doubly logarithm in the size of circuit. So this is so even work with low norm A and the identity matrix is sufficient to get optimal broadcast encryption. So for the rest of this talk for now, we're going to work with I and just focus on getting optimal broadcast encryption.
So it's circuits with large span naturally.
Yeah. If you think of it, arithmetic circuits, easier to think of. The fan in is going to be N.
And the construction can handle large span, and I guess it can.
Yeah, the only interesting circuit I know with extremely small depth is broadcast encryption.
No, but I'm saying the BGP plus construction can handle gates with large span in.
Yeah, you can handle. Yeah. Roughly speaking, your depth is much bigger than that. Your size, your addition gates are for free, essentially. And you multiply by the size. Yeah, but that's fine. Yeah, your fan is going to be N, so the growth is going to be N, but your noise growth is logarithmic in the fan. So this is going to be okay. So this is doubly logarithmic. This is doubly logarithmic in N. This is N, and this expression basically you get an N here and an N here, and then you get log N. Oh no, sorry, you get N here and a log N there.
How is this different than the original ID? Like why is it like 2 to the depth rather than?
Because my noise growth is doubly exponential in depth instead of exponential in depth.
Why? What this looks like?
With the identity matrix, because I don't get to do the G inverse anymore.
I see.
So every time I do a multiplication, instead of multiplied by security parameter, I square the noise.
It's like 9 ESW without the gap.
Yeah. So instead of A1 times G inverse of A2, I just do A1 times A2. So here the norm would be this is always small, So this is fine, but here both are going to be big. Any questions? Okay, so far so good. So what we have roughly showed is that, so we need to modify our scheme. It's going to look a bit like this now. And what I've shown so far is that, the product of the ciphertext and secret key are pseudorandom.
Sorry, there's nothing inherent here that prevents you from using the decomposition, or in other words, G inverse.
Yeah, sorry.
There's nothing inherent that prevents you from using G inverse here, right?
There's nothing inverse. No, this statement.
You want it to be low norm, right?
I need A to be low norm.
No, you have the G, and then you have identity, and you have everything in between. You know what I mean? Like there are gadget matrices that allow you to bit decompose small numbers with small, it grows from, so.
I'm not sure. Maybe we should take it out. Okay. But certainly, right now, I do use the fact that A has low norm to prove this statement.
Yeah, start with small powers 2 and.
But I do use it right now. Maybe there are ways around it, but this is why I use it. Just any questions? Okay, good. So far I have shown that the product of the ciphertext and secret key is pseudorandom. Whereas what I really want is to show that the ciphertext is pseudorandom given the secret keys. So there's a gap between the two of them. And now our basic intuition is that we really want to deduce the fact that the ciphertext is pseudorandom given the secret keys from the fact that the product of the ciphertext and secret key is pseudorandom. And our basic intuition in general is that if I give you, so the ciphertext of this form, the secret key of this form, and our basic intuition is that if you're given an LWE sample and some Gaussian pre-images, the only thing that the algorithm really learns is the product of the two quantities. So basically all known attacks, roughly speaking, falls into this category. And if this is true, this basically says that, the only thing you can do with the ciphertext given the secret key is to multiply the two of them together. I've already shown that if you multiply two of them with pseudorandom, then the decomposed version is pseudorandom. Okay, and to formalize this intuition, we're going to put we formalize this intuition via a new lattice assumption, which is basically what we call evasive LWE, and it's also proposed independently by Hoeteck. I should talk about that. Yeah. Okay. So, but the version here is simple for broadcast encryption. Okay, so roughly speaking. This is what, roughly speaking, the evasive LWE assumption looks like. This is given some distribution P. P corresponds to this A minus extensive G's in our application. The assumption says that if SB plus E and SP plus E prime is pseudorandom, then SB is pseudorandom given B inverse of P. So it captures the idea that if given this expression and given this expression, if you multiply them together, they are pseudorandom. Then if you separate them, it's still pseudorandom. Right, and we needed to hold given B and P. Okay. Let me give you some examples. So for instance, if P is a uniform distribution, then you can actually show both the precondition and the postcondition from the LWE assumption. Okay. So true implies true, so the statement is true. Whereas if B is the gadget matrix, then the precondition is false, the postcondition is also false. So there's no contradiction. Okay. So now we have a pop quiz. Let U be the uniform distribution. Okay, consider the following three P's. The first is uniform concatenated uniform. The second is uniform concatenated uniform. One is left, right, the other one is top, bottom. And the third one is uniform concatenated with the gadget matrix, top and bottom. Okay. So for this P, all right, is this statement true for each of these three P's? Okay, so we have a pop, let's do a quick pop quiz. It's okay to be wrong. Who thinks that the first one is true? Okay. Who thinks that the second one is true?
What's the question again?
Okay, good. P, U is a uniform distribution.
Yeah.
I give you three examples for P. And for each of these examples for P, is SB pseudorandom given B inverse of P.
Are you asking only about the post condition or like both?
Just the post condition.
Okay,
just the post condition. Okay, that's the question. So we know that the post condition is true if P is random. Okay, what if P is sort of a structured random?
So what is the difference in the first two matrices? Is it uniform and the other one is uniform?
U is uniform. The first one is two copies of same uniform.
Oh, same uniform. Oh, okay.
Yeah, the same uniform. Two copies of same uniform. The second one is two copies of same uniform stacked top and bottom. So this means that I give you, like B1 and B2, and then B times B1 is U, B times B2 is U. This one says that, in the first one, basically I want B times B1 equals to U, and B times B2 equals to U. That's sort of what's happening in the first one. In the second one, I basically have B times B1, B2 equals to U.
So P is obviously not good.
Sorry? Okay, let's try again. Okay, so who thinks the first one is true?
What does true mean?
Sorry? That S times B plus B super random given B inverse of C.
No.
Okay. Who thinks the second one is true? Who thinks that one is true?
Feels like it's.
Well, no one thinks that one is true.
Also,
Okay, all right. So
That's good. That's good. Good.
that's true. Okay, so turns out the first one is false as an explicit attack, and the second and third one you can prove from LWE. The first one is false because basically you basically can collect a basis, an I-type basis for B. And indeed, if you check with the precondition, it will be easy to see that the precondition is false for the first one. Because when you multiply by P, you get the same thing appearing twice, more or less. So it's not pseudo. For the second one, it's not hard to see that you really get an LWE sample where the secrets add up. For the third one, you basically get LWE sample from the top part that will mask the gadget in the second. So the left half of S is going to be LWE sample. So so these things are highly non-trivial statement. Even just to predict whether I think this is even useful just as a predictor for which P this is. So as far as I know, this is the best predictor.
You're saying these are examples of matrices where the heuristic is actually true.
The first one is false, and the precondition predicts it. This
That's right.
These three are all examples of distribution that the precondition predicts the correct.
Right.
But that is, so this is an if-then statement.
Yes.
But you just showed us a bunch of if and only ifs.
Good. So not quite if and only if. Okay. So the first one is false.
Yeah.
So the post-condition is attack, the precondition is false.
Yeah.
So it doesn't contradict. False implies false doesn't contradict.
No. I'm saying in all cases you have an if and only if, right? But I don't know if it's always an if and only if. It was always either the precondition was false and the postcondition was false, or the precondition was true and the postcondition was true.
Yeah.
It's never false true.
I see. Okay, assuming LWE.
Yeah.
Okay, yeah. I never had a. So you don't want a true implies false because that will contradict it.
Yeah.
But false implies true is. I don't know about example of false implies true.
I see.
I didn't try super hard. Yeah, I didn't think about that. Let's think about that. So the first one you have explicit attack. The second and third one you can prove without LWE. The reduction is actually somewhat non-trivial. This one turns out to be slightly easier. This one requires a bit more care. And in fact, we can prove a more generalized version like U and something related to U and.
If you fix P rather than distribution, consider P to be fixed. If P is fixed, so how is fixed? Is this trivial or?
If
P is
P is fixed. Not a distribution, but
if P is fixed.
P is fixed.
If not distribution.
But not a distribution. It's probably false for a worst case P. P is fixed in the sense that it's fixed matrix.
So the assumption you're not assuming that this holds for all distributions.
Okay, good. So think of it as a heuristic. I think of this sort of like a generic.
So
model.
the application will induce a
specific. Yeah, for the application will go with specific P. Yeah, that's correct. But the P is slightly complicated. It looks like a combination of these two, but even more.
So can you make a conjecture about which fixed matrices P this?
For the scheme, we only need this to hold for specific distribution.
No, but fixed without distribution. Which fixed matrices P or fixed?
No, the distribution P will depend on the evaluation.
Fixed P, right?
Fixed P, the precondition is false.
Exactly.
That's true.
Exactly.
You're saying you're the assumption.
By fixed, I don't mean
like 1, 2, 3, 4, 5, 6, 7, 8, something like that, right?
data name matrix.
Anyway,
So it's a question about what the word fixed means. It's not
no,
about
no, no,
fixed.
no.
Think of this one as take the distribution.
Yes, a singleton distribution, right? It puts mass on one matrix and that's it. Yeah, so that's what fixed matrix means. Okay, so let's say P is the matrix 1, 2, 3, 4, and then 5, 6, 7, 8, and then that's the what happens to the assumption is the question. Daniel's answer is that the precondition is false.
And precondition is false, yeah.
Correct.
So
That's it. That's it. End of story.
yeah.
You're making the assumption on all distributions, including singleton distributions, right? You're making the assumption for all P's. You don't need it for all P's, but right now you're saying.
Yeah, only for all P, but for the scheme, you only need a partial distribution. That's the question.
Right. So just to be clear about non-uniformly, the precondition is broken. Right?
Yeah. Okay. So the question doesn't make sense for fixed.
No, it does make sense, but
Yeah.
but the assumption is okay. For fixed.
Non-uniform.
Non-uniform. Yeah.
Yeah, I mean, you also need, some auxiliary input. So let's zoom into this assumption a little bit. And let me first observe that the precondition is saying something slightly stronger. Okay? So in the post condition, you can always take SB plus E and multiply by V inverse of P. Okay? And I want to say that the precondition is something stronger. It's not saying that this expression is pseudo-random. It's saying that SP plus S times P plus fresh noise is pseudo-random. And these two things are two different things because in fact, this quantity has low rank and this quantity. These two distributions are clearly distinguishable. So the assumption doesn't just say that the only thing that the observer can do is to multiply the two quantities together. It says that even if you're given a little bit more noise, that's the one for which the precondition applies to. Okay? So the way to interpret the precondition is really, it roughly says that if you multiply these two quantities together, and the higher order bits are pseudo-random, then the post condition is true. That's one way to justify having to add fresh noise to do. This is a bit technical, I can. Let me just say that also the precondition is what allows you to avoid generalizing attacks in the literature on IO candidates and all these other ones. So let me move on because I only have 5 minutes left. Right, for the application, we need some additional matrix A prime. Okay, so I'm almost done. Okay. So this is our scheme. Okay. So combining the evasive LWE assumption and the previous statement that we proved from LWE, you can prove that your ciphertext is pseudo-random given the secret keys. But what we've done so far is we've ignored the cam. If you put the cam back into the picture, the proof breaks down. Okay? Because the proof uses the fact that R from S is pseudo-random. But now in the cam, S also shows up. So now this statement is no longer true if you're given S times A sub. So to fix this, well, turns out what's true is that if there's an extra Ri here, then this statement is true from LWE. And you can basically make sure that this appears in the proof by modifying the scheme and masking the cam key with extra LWE set. And then once you do this to satisfy correctness, you need to add a couple more terms to your ciphertext secret key. For those of you familiar with the prior works, essentially you're doing some kind of IPFE to make sure that you're basically doing IPFE where you encrypt this and give me out secret keys for R so that all you learn is to put out these terms.
Inner product functional encryption.
Yeah. But I don't know how to prove it as an inner product functional encryption because it's not evasive. But if you run the reduction, that's just what's happening. So right. So in particular, this is essentially our final scheme. So it's still quite simple. So assuming the evasive LWE assumption for sub-exponential noise homogeneous ratio and LWE itself, this gives you an optimal broadcast encryption scheme. And moreover, if you take, and this is for A that's low norm, and if you make A high norm and replace I with the gadget matrix, then we get a CPAB for circuits with short ciphertext, but we need to make an additional assumption. The assumption is basically this, which says that, so when A is low norm and this is I, we know how to prove it LWE. This say that this is pseudo-random even when A is high norm and G is the gadget matrix. So this extra assumption that we need. The thing about this assumption is qualitatively different from evasive LW. It doesn't talk about Gaussian trapdoors, and it also doesn't talk about functions f. Okay, this is for all x. So right, so that's sort of and this is the final CPAB. So it's still very simple. So to conclude, all right, so I talked about broadcast encryption, CPABE, and evasive LWE, and I think there are a lot of very nice open problems. If you're a cryptanalyst, you can try to break evasive LWE. If you're into lattice problems, you can try to do reductions. Okay. If you're into advanced crypto from LWE, you can either try to find new applications for this evasive LWE assumption. So in fact, Lothar will be talking about how to use assumption to build our witness encryption. We also have independent work with a similar result. And also, I think another nice open problem is to get CPAB for circuits from just evasive LWE. In particular, can you get rid of this extra assumption? Which I guess Vinod was already suggesting an approach. I think this should be quite good. Thank you.
We have time if there's any questions.
So maybe just is there hope to formulate? I know it's a very good question. Is there hope to formulate some Uber assumptions similarly to the ones that have been made in the context of group-based assumptions? Is there any hope to formulate a clean Uber assumption?
Uber assumption. Yeah, the closest I know, which is not false, is the evasive LWE assumption.
I see. I meant something that is even more general that would imply, but the evasive LWE you're saying. So what other applications would it simplify other things?
So with evasive LWE, the only hope you can use it to use it for is to build primitives that are evasive. And right, so for instance, witness encryption is one of them, and also ABE-like objects. In general, in a non-evasive setting, the assumption is broken, and usually the scheme may be broken also.
Yeah.
So if you, it's very important that when you multiply by p, the joint distribution is random. So if there's any structure whatsoever that's detectable, for instance, when you have uniform followed by uniform, there's usually even an attack on the. So as far as I know, so for instance, I tried to build some other objects, and I couldn't prove it under evasive LWE because S times p is not pseudo-random, and for that scheme. I actually have, if you think a bit more, you can actually come with it.
But maybe listen, so the assumption is that you said that the assumption is not that it holds for every distribution P, right?
Right, for specific distribution P, yeah. So if you have a scheme, and then the P has a particular distribution.
Okay, so maybe an Uber assumption would say that for every P that satisfies a certain simple condition.
Yeah, that's Uber assumption. Yeah.
I'm confused. The assumption here says for every distribution P, if A is true, then B is true.
So there is no counter. You're saying there is no contrived counterexample for this.
That's what he said. Yeah.
There's no counter.
That's right. That's right.
The way I interpret this, is, I think of this. If you think about it as generic pairing groups, I think of this as quantities in G1, and I think of this as quantities in G2. And this assumption basically says that the only attacker are the ones that take things in G1 and G2 and multiply them together to get objects in entirety. So in generic model, we can prove that these are the only attacks. But here, we don't even know. In fact, these are not the only attacks in our real world. But if you pair everything together and the joint distribution is pseudo-random, which is roughly what the precondition says, then in those cases, that seems to be the only attacks. So just in particular, this is an example of something that happens. When you multiply everything together, you have correlation in target group. When you have correlation in target group, usually the post conditions are no longer true. And in the sense of no longer true but explicit.
There a plausible generic model, even like a very coy generic model in which something like this holds?
Yeah, that's a great question. We don't have good generic models for everything. I think that's a very nice.
What if you like really weaken like a real toy model? Like it might be interesting even if like this bears almost no relationship whatsoever with the actual assumption, right? Just to show model that sort of represents this behavior?
Yeah, I think that's a good question. We don't have good models for LPN. We do, I think. LPN, I think Duval and Ilet and friends have some sort of a model that seems to capture LPN type attacks. In LPN type attacks, I think basically all attacks roughly speaking are the form that tries to solve this. That says that if you can solve this, the only way you can break LWE is to solve this. That's sort of what happens in the LPN, and that is sort of but here, in fact, the precondition says that this is hard with respect to P. So in fact, this distribution has a case that this is easy, and this this is hard. So the precondition roughly says that, so it had a flavor of saying if this is hard, then LWE is hard. Yeah, provided S is uniform. So you can have cases where if S is low norm, then you can have the case that this is hard for P, but the post condition is false. For instance, if P is a low norm matrix, then this holds, and then S times low norm is still pseudo-random if S is uniform. But if S is low norm, then the product is low norm, then it's clearly differentiable.
Great, let's thank Hoeteck.